Tonight, we're going under the ice of Europa without going anywhere. I want you to imagine you're standing on it, on this blindingly bright, airless plane of water ice, floating out there in Jupiter's orbit. The sun is a harsh, distant spark. Jupiter hangs in the black, like a striped, planet-sized warning sign. And under your boots, there's not rock. There's a frozen lid on an ocean that might hold more water than every sea on Earth combined. Up here, you can see everything. The cracks that run for thousands of kilometers, the ridges, the chaos terrain, the faint bluish stains where fresh ice has welled up from below. We've mapped these in exquisite detail from millions of kilometers away. We can trace individual fractures only a few tens of meters wide. We can measure how bright the ice is, how the radiation from Jupiter has baked and sculpted it. And yet, the ocean under your feet, that's almost a rumor, a physics-based ghost story. Because here's what nobody tells you. When people say Europa is an ocean world, you picture a place we understand. The way we understand Earth's oceans from satellites and sonar and ship logs. You know the one. Cutaway diagrams with a nice blue layer under a thin white shell labeled Global Ocean. Very tidy, very certain. But the reality is that the ice, the part we never touch, is the part we know best. The water, the part everyone cares about, is mostly invisible to us. We can photograph every crack in the ice, but we have never seen a single wave in that ocean. We only infer it from clues. A magnetic field that twitches as Europa moves through Jupiter's. Chemistry on the surface that hints at salty water below. Heat flow models that demand something liquid down there to carry the energy away. It's like trying to reconstruct an entire sea from the way a ship's mast sways in a few drops that splash over the rail. So here's the paradox we're going to live in tonight. The most promising ocean for alien life in the solar system is one we may never actually see. How can something that might be 100 kilometers deep, holding twice Earth's ocean volume, be more hidden than an ice shell that's maybe only a few tens of kilometers thick? How can the thin lid be an open book while the vast interior stays closed? So, let's start at the very beginning, layer by layer. Atmosphere, ice, ocean, rock, core. Because the moment we peel Europa apart in our minds, you'll see why the ice gives up its secrets to cameras, to spectrometers, to gravity measurements, while the ocean fights to stay invisible. Now let's begin. So here's the weird part. The more we peel Europa apart in our heads, the more lopsided our knowledge becomes. We have this razor-sharp picture of the lid, the ice you can't miss. From telescopes on Earth and from spacecraft like Galileo, we've mapped those reddish cracks and looping scars at resolutions down to tens of meters. We can trace individual ridges across hundreds of kilometers. We can measure how bright the ice is, how it reflects sunlight, how radiation from Jupiter bakes its surface chemistry into something like a frozen crime scene. The ice is loud. The ocean, silent, invisible. It doesn't show up in any photograph you've ever seen. Because here's what nobody tells you. The part of Europa that might actually be alive is the part we never see directly. That global ocean, hidden under something like 5 to over 30 kilometers of ice, only shows up as hints in gravity data, in tiny wobbles in Europa's orbit, in a magnetic field that shouldn't be there unless something salty and conductive is sloshing around inside. Why does that matter so much? Because that invisible ocean is not a little underground lake. It may hold more than twice the volume of all Earth's oceans combined. On a moon barely a quarter of Earth's size, you get an ocean world that puts our blue planet to shame. If you're going to bet on life beyond Earth, you don't ignore the place with the most liquid water in the entire solar system. And yet, something is above the planets. Something is below them. We obsess over the glittering surfaces in the sunlight, but the real action is in the dark, pressurized layer we can't photograph. Europa's ice shell, in planetary terms, is almost decorative. A thin, fractured veneer a few tens of kilometers thick, wrapped around an ocean that might plunge 100 kilometers down and circle the entire moon. The ratio is absurd, a brittle crust on top of a planetary scale abyss. How long has that abyss been there? Quite possibly billions of years. Long enough for chemistry to keep trying new combinations, over and over. Long enough for energy from tidal flexing, from rock-water reactions at the seafloor, to drive cycles that look suspiciously like metabolism. Somewhere in that darkness, did chemistry cross the line into biology? And if it did, what does it look like when evolution plays out in eternal night? The cruel part is that we're stuck reading the scratches on the lid. Those chaos terrains, those double ridges, those weird stains of salt and oxidants on the surface are our only direct pages of the story. We're trying to reconstruct an entire hidden ocean from its fingerprints in the ice and its whispers in Jupiter's magnetic field. So where do we go from here? In the next part, we'll follow how scientists turn magnetic whispers, tiny tugs and spacecraft trajectories, and hints of water plumes into a three-dimensional picture of an ocean they can't see at all. Now let's begin to make that invisible ocean visible. Before we go any deeper into that invisible ocean, can we make a quick deal? If the idea of hunting for an ocean you will never see with your own eyes is even a little bit thrilling, this is the exact moment when your click actually matters. A like on this video, a quick subscribe, takes you half a second. It costs you nothing. But to the algorithm, it's like flipping a bright switch that says, more of this, more hidden oceans, more weird gravity detective work in space. Because here's what nobody tells you. Episodes like this, where we chase faint magnetic whispers and tiny wobbles in an orbit around Jupiter, only get made if the last ones performed well. Your like is literally a vote for more deep dive breakdowns of places textbooks mention once and then forget. You know the one, the icy moon that's always the side character in a solar system diagram, never the lead. So if you're into the idea that somewhere under that ice there might be chemistry writing its own alien story, hit like. If you want to see us map not just Europa but Enceladus, Titan, Pluto, and the weird dark comets at the edge of the solar system, tap subscribe so you don't miss when we go back to those worlds. And here's the low effort, high impact part. One click from you nudges this video a little higher above the endless flat plane of recommended content. That tiny nudge is enough for the platform to show it to more people who care about oceans in the dark, about radiation-blasted ice, about what gravity is doing in the shadows. You're not just helping this channel, you're helping build a tiny, very nerdy cloud of people who want to think about Europa at 2 a.m. Now for the question I really want you to answer in the comments, because this is a genuine dilemma for planetary science. If we ever get the chance, should humanity actually drill through Europa's ice to touch that ocean, risking contamination? Or should we stay in orbit and fly by, keeping the ocean pristine but forever out of reach? Do we protect the laboratory, or do we open the door and look inside? What would you choose if you were the one signing off on the mission? We read those comments. We argue over them. And yes, we use them to decide which worlds and which hidden structures get a full-length breakdown next. Your likes and your ideas are how we pick the next target in this three-dimensional picture of the solar system. So, let's start at the very beginning of Europa as most of us imagine it. Because now that we've made that deal, we're going to take that familiar mental model and quietly dismantle it. So, let's start at the very beginning of Europa as most of us imagine it, because the picture in your head is already doing quiet work on how you think. You know the one. The classic classroom poster, the sun blazing on the left, the planets lined up like beads on a wire, all marching across a perfectly black background. Slide your eyes to the right along that flat line, and there's Jupiter. Huge and striped, with 4 tiny dots circling it. In the neat version, those moons are drawn like marbles on a table, each orbit a perfect ring in a single, razor-thin plane. No tilts, no eccentricities, no chaos. Just clockwork. One of those marbles is labeled Europa, and that label already feels like a complete sentence in your brain. Now we zoom in. Europa becomes its own glossy sphere in the diagram. A small, smooth, white-blue marble with a few reddish-brown cracks drawn in for drama. Icy moon, subsurface ocean, orbiting Jupiter in a flat plane. That's the whole pitch. Because here's what nobody tells you. Once you've seen it drawn that way a dozen times, your brain quietly files Europa under solved problem. The cross-section makes this even stronger. Textbooks love that layered cartoon slice, the one that looks like a tidy geological cake. On the outside, a whisper-thin atmosphere, barely more than a caption. Then a clean ice shell, drawn as a simple white band of fixed thickness. Under that, a perfect blue ocean band, wrapped evenly around the whole world. Beneath that, a gray rocky mantle, and at the center, a shiny metallic core. All stacked, all centered, all shown in a single flat slice through the middle. You can almost feel the implication. We know where everything is. Ice up here, ocean right below it, rock under that, metal in the middle. The diagram is like a map you could print on a coin and slide across a table. Europa's orbit is flat. Its interior is drawn as flat layers. Even the way Jupiter's system is shown, rings of moons like grooves on a CD, locks you into this two-dimensional mental model. And yet, something is above the planets. Something is below them. Even here, in the Jovian system, orbits are tilted. Shells are uneven, and the real ocean doesn't sit in a perfect cartoon band. But the poster doesn't mention that. It doesn't mention that the subsurface ocean label is really a hypothesis built from gravity measurements, magnetic whispers, and a lot of uncertainty. So when you look at that flat picture, it feels done, finished. We know Europa. But do we? In the next section, we're going to start pulling on the edges of that diagram and watch how quickly that comfortable layer cake begins to tear in 3 dimensions. So let's actually pull on it. Let's take that neat little Europa cross-section you've seen 100 times and watch it come apart. You know the one. A perfect circle sliced open with crisp color bands, white ice on top, blue ocean in the middle, brown rock at the bottom, maybe a tiny metallic core for extra drama. It looks so clean that your brain quietly files it under known. Because here's what nobody tells you. That picture isn't exactly wrong, but it's doing a magic trick. It's smuggling in a whole cargo hold of assumptions that reality has never signed off on. Look at how smooth those layers are. The ice shell is a uniform thickness. The ocean has a flat ceiling and a flat floor. The rocky mantle is a simple curve. That's not data. That's graphic design. In real space, gravity, heat, and time do not care about your tidy bands. Ice can be thick in one region and thin in another. There can be buried ridges, voids, slush pockets, and frozen icebergs locked in place long before you ever reach the liquid water. But because we've been exposed to that same cross-section over and over, our intuition gets tricked. We feel like we've actually seen Europa's ocean. We haven't. We've seen an artist's impression built from magnetic whispers, gravity tugs, and models. No camera has looked into that water. No probe has watched those currents. And yet, in your head, that blue strip feels real, like a photograph. So, let's start at the very beginning of the counterfactual. Imagine you could point a spaceship straight down and fly through Europa like it's a level in a video game. You punch through the surface ice. Do you see a glowing, uniform white band? No. You'd pass through unknown thicknesses of fractured plates, chaotic blocks, perhaps lenses of half-melted slush, pockets of brine, frozen caverns where the radiation-processed surface has been buried. At some point, if the models are right, you hit liquid, but even then you wouldn't see a neat blue stripe. You'd see darkness, turbulence, and an ocean whose true depth and circulation we can only guess at. Here's the hidden assumption the diagram sneaks in, that once you leave the visible ice, there's nothing interesting until you hit rock. Just a featureless, uniform ocean layer, a blank middle. But oceans on Earth are anything but blank. Chemistry changes with depth. Currents carve invisible highways. Heat sources turn specific regions into power plants for life. So what if almost everything that matters for life on Europa, the chemistry, the heat sources, the circulation, is buried in the very details those flat diagrams erase? And yet, something is above the planets. Something is below them. In the next section, we're going to stop treating Europa's ocean as a single blue band and start treating it as a three-dimensional world that could be as varied and as surprising as the entire solar system in miniature. So let's take that seriously. If Europa's ocean is a whole miniature solar system of complexity, what would happen if we tried to punch straight through it? Imagine this impossible machine. We land on Europa, pick a random spot, and start drilling a perfectly straight shaft down toward the center. No engineering limits, no budget, just a clean cut through ice, ocean, and rock. You know the one, the textbook cross-section that shows a neat white layer, a blue band, and a rocky core? We're about to find out how wrong that picture really is. At the surface, the drill bites into brittle ice. It's bright, almost painfully reflective, one of the shiniest skins in the solar system. Radiation from Jupiter has baked the top few centimeters into a chemically weird frosting, full of broken molecules and oxidants. Cracks and ridges crisscross the landscape, so the upper tens or hundreds of meters are probably a chaotic mess of fractures, voids, and refrozen pockets. It's less a clean sheet of ice and more like shattered safety glass that's been squeezed back together by gravity. Keep going. Deeper down, the pressure and temperature rise. The ice stops behaving like the crunchy snow you can imagine under a boot and starts acting more like very cold, very slow taffy. It creeps. It flows. Over thousands of years, it can bend around obstacles the way rock does in Earth's mantle. So where exactly does ice shell end and ocean begin? Is there a sharp boundary or a slushy, convecting transition zone that would make our neat blue line look embarrassingly flat? Because here's what nobody tells you. We don't even agree on how far our impossible drill would have to go before it hit liquid. Some models say the ice might be only about 5 kilometers thick in places, thinner than the distance from your house to the other side of a big city. Others put it at more than 30 kilometers, thicker than Earth's entire crust under some continents. That single uncertainty completely changes how reachable the ocean is, how much energy can move through the shell, and how easily the surface and the deep interior can talk to each other. Now let's overshoot the ocean and head all the way to the seafloor. What are we actually drilling into down there? A smooth basaltic plain like the deep Pacific? Towering mountains of frozen rock built where the interior once flexed and cracked? Or a landscape lit by hydrothermal vents with hot mineral-rich water blasting out of chimneys the way we see at Earth's mid-ocean ridges? The problem is that every answer we give is filtered through gravity measurements, magnetic wiggles, and a few flybys from the Galileo spacecraft. We're reading faint signatures and trying to reconstruct an entire alien geology from them. And yet, something is above the planets. Something is below them. We can't actually dig that shaft through Europa. So how can we be this confident there's an ocean at all, and not just warm, squishy ice pretending to be one? In the next section, we're going to follow the clues hidden in Europa's gravity and magnetism and see why scientists are willing to bet on an ocean they've never seen. So here's what this video is really trying to do to your brain. Up to now, Europa has probably lived in your head as a simple cartoon. White ball of ice, thin blue band labeled ocean, rocky middle, maybe a tiny core. You know the one. It's the Europa version of that flat solar system diagram from school. Clean, layered, comforting. But what if that tidy picture is quietly lying to you about where the real mystery is? When you imagine Europa, what do you actually see first? The cracked ice, the smooth plains, the orange streaks. Why does almost every diagram give you a crystal clear slice through the moon, as if someone really did dig that impossible shaft? And what crucial parts of the ocean's hiddenness does that neat cross-section erase from your intuition? Because here's what nobody tells you. Those layers are not all equally real in our knowledge. The ice, the ocean, the rock, the core do not sit in your head with the same level of certainty. The goal of this episode is not to dump a pile of Europa facts on you. It's to quietly upgrade that mental model from a flat, labeled disk into something more three-dimensional, more uncertain, where you start thinking like a detective reading clues in gravity and magnetism. So, let's start at the very beginning of that upgrade. First, we're going to rewind the clock and ask how Europa ended up with ice on top and liquid below it all. How does a moon form in the gravity well of a gas giant, in a miniature version of the solar system's own disk, and still keep enough heat and salt to run a global ocean that might be deeper than anything on Earth? Then we'll tackle the really unsettling part. How do we know there's an ocean when we have never seen it? We'll follow Galileo's magnetometer as it flies through Jupiter's magnetic field and feels an induced field from a salty, conducting layer inside Europa. We'll connect that to chaos terrains, to heat flow models, to chemistry on the surface that shouldn't be there if this were just cold, solid ice. Third, we're going to ask why the ice feels easy and the ocean feels stubbornly invisible. Telescopes can map Europa's cracks from Earth. Future spacecraft will skim just above that bright scarred shell. But the ocean, no camera sees it, no radar gets a clean snapshot. It shows up as wobbles in orbit, tiny tugs in gravity, magnetic whispers. By the end, when you see any Europa diagram, we want you to instantly sense which parts are rock solid, which are best guesses, and why the ocean is still the most hidden layer. Now let's begin the real dive. Europa's birth, the magnetometers, the plumes, the future missions. And yes, the ethics of touching an alien ocean we can't yet see. So if we're going to dive into a hidden ocean, we have to rewind before there was even an ice shell to hide it. Before Europa, before Jupiter, before the solar system had any tidy, flat picture at all. So, let's start at the very beginning. Roll the clock back about 4.6 billion years to a cold, dark, rotating cloud of gas and dust in interstellar space. You know the one, the kind you see in Hubble images, glowing faintly, looking peaceful and harmless. It wasn't. Gravity started to win. The cloud collapsed inward, spun faster, and did the same trick you saw in the earlier section. It flattened into a huge disk around a forming sun. Because here's what nobody tells you when they show you that simple diagram. That disk wasn't just the birthplace of the planets. It was also the backdrop for a second, smaller drama out in the cold, where Jupiter was coming together, far from the newborn sun, where temperatures dropped and water could freeze. The material in the disk changed character. Closer in you got mostly rock and metal. Out here, ice joined the party. Europa didn't start as a neat frozen ocean world. It condensed from this mixed inventory of water ice, rocky grains, and metals swirling in the outer regions of the early solar nebula. Imagine billions of icy pebbles and boulders colliding, merging, shattering, and merging again. As Jupiter grew, it didn't just sit there as a lone giant. Its gravity carved out a sub-disk inside the larger solar system disk, a miniature version of the whole thing. Gas and ice and rock orbited Jupiter the way the planets orbited the Sun, all in a relatively flat plane defined by that spinning material. In that tiny clockwork, the Galilean moons were born. Europa formed in this Jovian nursery, not as a pure ice ball, but as a layered object from the start. Denser rock and metal sank inward. Lighter water ice floated toward the outside. That composition, rocky interior wrapped in an ice-rich shell, quietly set the stage. Because once you have rock, you can have radioactive decay and tidal flexing. Once you have ice, you can have melt. But here's the catch. It's one thing to melt ice once. It's another to keep a global ocean liquid for billions of years while orbiting in the deep freeze of the outer solar system. How do you keep that water from locking up solid, top to bottom? How does Jupiter's gravity, Europa's orbit, and that layered interior team up to power an ocean you never see? In the next part, we'll follow the heat and watch the ice shell turn from a simple crust into the moving, breaking, concealing lid of a hidden sea. So if Europa is orbiting in this brutal deep freeze, why isn't it just a solid ice cube ball all the way down? How do you get a global ocean hiding under a crust when the sunlight out there is so weak it barely warms the top frost? So, let's start at the very beginning. At Jupiter's distance from the Sun, the equilibrium temperature of a bare ice surface is around 160 to 220 degrees Celsius. Cold enough that, left alone, any water should lock up from surface to core and stay that way for billions of years. No cracks, no liquid, just a frozen moon following a quiet orbit around a giant planet. But Europa was never truly left alone. Because here's what nobody tells you when you see that smooth white picture. There's an entire power plant hidden inside this tiny world. Some of that power is ancient. When Europa first formed out of the collapsing cloud of rock and ice, impacts and compression heated its interior, and it's been slowly leaking that heat into space ever since. Radioactive elements in the rocky mantle keep adding a steady background glow, like embers that refuse to go dark. If that were all, Europa would still probably be a frozen rock by now. The real trick is gravity. Europa is close enough to Jupiter that the planet's pull is dramatically stronger on the near side than on the far side. As Europa moves along its slightly stretched or eccentric orbit, those tidal forces change. The whole moon gets squeezed, then relaxed, then squeezed again. You can picture it like this. Take a paper clip in your fingers and bend it back and forth. At first it feels cool and rigid. Keep going and it starts to warm, not because you added fire, but because metal crystals are rubbing and flexing inside. Europa is that paperclip, except it's the size of a small planet and Jupiter is doing the bending every orbit. Inside the ice shell and rocky mantle, that constant flexing becomes frictional heat. Rock grinds, ice deforms, pockets of material partially melt, and yet something is above the planets, something is below them. In this case, what's above is the dead, frozen surface that you can see. What's below is a warm, restless interior that refuses to stay solid. There's one more twist. Europa doesn't orbit Jupiter alone. It's locked into a gravitational dance with Io and Ganymede, a three-body resonance that tugs on Europa's orbit every lap and keeps it slightly eccentric. The tides can never quite settle down. The flexing never fully stops. Add all that up, and you get a delicate balance. Enough internal energy to melt a global layer of water beneath the crust. Not enough to blow the ice apart. The surface stays frozen and bright for our telescopes, while the ocean beneath keeps rolling in the dark. In the next section, we'll see how that hidden heating doesn't just make liquid water. It sculpts the very fractures and chaos terrains that let us read Europa's ocean from orbit. That hidden heating doesn't just melt a little puddle under the crust. It rearranges an entire world. It takes Europa from a frozen snowball into a layered planet with boundaries, pressure, and secrets stacked on top of each other. So, let's start at the very beginning. When Europa formed in the young solar system, it was a chaotic mix of ice, rock, and metal orbiting inside Jupiter's gigantic gravity well. Radioactive elements warmed it from the inside. Tidal flexing kneaded it from the outside. And all that energy did something crucial. It let the moon differentiate. Differentiation is what happens when a world gets hot enough for its ingredients to move. Heavier materials like iron and nickel sink inward. Lighter silicates float above them. Water and ice rise even higher. Because here's what nobody tells you. That simple game of cosmic density sorting turns a messy ball of material into a cleanly stratified interior. And it quietly decides which parts of a world you'll ever be able to see. Deep in Europa, that process likely left a metallic core at the center, wrapped in a rocky mantle. You can picture it as a miniature version of Earth's interior, just colder and smaller. Above the rock, though, Europa does something Earth can't. It carries a global shell of water 10s to maybe 100 kilometers thick, all stacked in different phases that only exist under intense pressure. Closest to the rock, where pressures are enormous, water may freeze into bizarre, high-pressure ices that are denser than liquid. Above that, where the pressure eases but the heat from below still wins, a global liquid ocean can persist. Then as you move outward and the temperature drops, that ocean grades into the rigid surface shell, the cold, fractured ice we photograph from orbit. So the ocean isn't a simple blue band under a white lid. It's sandwiched between different kinds of ice, with complex chemistry at the rocky seafloor below and slow, grinding interactions with the overlying ice above. It's more like a living, three-dimensional volume than a neat layer in a textbook picture. You know the one, And yet, something is above the planets. Something is below them. With Europa, the above is that bright ice shell that reflects sunlight straight into our telescopes. We can map its cracks, measure its albedo, even taste a hint of its chemistry from plumes and sputtered particles in space. The below is the ocean, buried under tens of kilometers of opaque material that light can't cross and cameras can't touch. So how do we study a sea we can't see? If ice and rock are real physical barriers, what tools do we have that can slip through them, reading gravity, magnetism, and radiation without ever touching the water itself? In the next part, we start using those invisible senses, and Europa's hidden ocean begins to answer back. Those invisible senses are powerful, but before we dive into magnetism and gravity, we need to appreciate the one layer of Europa that doesn't play hard to get: the ice shell, Europa's most honest surface. From a distance, Europa looks simple, a smooth, bright cue ball hanging in Jupiter's glow. That brightness is our first big advantage. Its surface is mostly water ice with a very high albedo, around 0.67, which makes it one of the brightest solid worlds in the entire solar system. In the harsh floodlights of reflected sunlight, Europa practically overexposes itself. Cameras love this moon, because here's what nobody tells you. For planetary scientists, that brightness is free data. Point a telescope at Europa, and the photons just pour in. Even from Earth, observatories can resolve the global web of cracks and dark lines etched across that icy plain. With spacecraft flybys, it gets almost unfair. Galileo in the 1990s, and soon Europa Clipper and JUICE, can sweep past and photograph individual ridges, blocks, and pits at resolutions where each pixel is smaller than a city block. You're not guessing where the fractures are. You can literally trace them with your finger on the image. And those images aren't just pretty. They're geological field notes. We see double ridges that run for hundreds of kilometers, bands where the crust has pulled apart and refrozen, and chaos terrains where the surface looks like someone smashed a frozen lake, stirred the pieces, and let it all refreeze out of order. You know the one, that famous patchwork of broken plates that shows up in every Europa documentary. All of that is the ice shell telling us how it's been stressed, flexed, and rearranged from below. So, let's start at the very beginning of how we read that story. Sunlight hits Europa's ice, bounces off, and carries a spectral barcode back to our instruments. Split that light into its colors, and you get spectroscopy. Sharp dips and wiggles that reveal what the surface is made of. Water ice has a distinctive signature. Salts and other chemicals, things like hydrated sulfates or chlorides, add their own fingerprints. Without ever landing, we can say, there's water ice here, there are salts there. This region has been chemically altered. And yet, something is above the planets. Something is below them. The same is true here. Something is above Europa's ocean, and the ice records its influence. Tidal forces from Jupiter stretch and squeeze the moon, and the shell responds by cracking. Possible warm upwellings from the ocean push up, disrupt the crust, and leave chaos terrains and domes behind. The ice doesn't hide those events. It memorializes them in visible scars. In that sense, Europa's ice shell is like a readable skin, scarred, bright, and photographable. Of all the layers in this world, it is the least hidden. But if the skin is this talkative, what secrets are the bones and the buried sea still keeping from us? If the ice is a readable skin, the ocean is the organ we're diagnosing without ever seeing a scan. We have zero direct images of Europa's sea. None. No glowing blue caverns. No drifting plumes caught in the act beneath the crust. Everything you've ever heard about that hidden ocean comes from one thing: physics. Because here's what nobody tells you. When planetary scientists talk confidently about Europa's ocean, they're really talking about a chain of inferences built from gravity, magnetism, and a little bit of surface chemistry. We measure how Europa tugs on a spacecraft as it flies past, and from that wobble we sketch out how mass is layered inside. We watch how Jupiter's magnetic field sweeps through Europa's orbit, and we see a subtle, induced magnetic field push back. A global shell of salty liquid is the simplest way to make that happen. But a global shell of salty liquid is still a very rough picture. How deep is it? How thick is the ice above it? That's where things get messy. Some models put just a few kilometers of brittle ice floating over a deep world ocean, more than twice the volume of Earth's. Others argue for an ice shell tens of kilometers thick, with only a thinner water layer squeezed between the ice and the rocky mantle. Both can fit the limited data. Both can produce the gravity and the magnetic signature we see. So, let's start at the very beginning of how we even guess. You take what you know about rock, water, and ice under pressure, you spin Europa inside a computer, and you let gravity, heat, and rotation fight it out. Then you compare. Does this interior produce the same surface cracks we see in the real images? Does it flex and bulge in Jupiter's gravity the way our measurements suggest? If not, you tweak the thickness of the ice, the depth of the ocean, the temperature at the seafloor, and you run it again. And yet something is above the planets. Something is below them. In this case, what's below Europa's bright plane of ice is almost pure theory. Salinity, inferred from how strong that induced magnetic field has to be. Temperature structure, inferred from how fast heat must lake out to keep the ocean liquid over billions of years. Circulation patterns, inferred from chaos terrains that hint at warm plumes, and from surface chemistry that looks processed by oxidants drifting down from space. You know, the one thing we don't have? A direct measurement saying, here's a current, here's a shoreline. Right now, Europa's ocean is less an observed environment and more a self-consistent solution to a giant physics puzzle. It's the answer that makes all the separate clues stop arguing with each other. And yet, despite all this uncertainty, there is one line of evidence so compelling that most planetary scientists are convinced the ocean is real. So what did we actually measure out there in Jupiter's harsh magnetic shadow that made everyone sit up and say, there has to be an ocean? The answer came from one of the quietest instruments on one of the most overworked spacecraft we've ever sent to the outer solar system. Galileo wasn't flashy by the time it reached Jupiter in the mid-1990s. It was a veteran probe doing repeated flybys, looping through Jupiter's gravity well, stealing just enough momentum to skim past moons like Europa again and again. On board was a small, unassuming device, a magnetometer. Its whole job was to measure magnetic fields in space, to trace invisible lines that never show up in the pretty flat diagrams. You know the one. Planets on rails, maybe a few rings, but no hint of the magnetic chaos blasting through that picture every second. Because here's what nobody tells you. Around Jupiter, magnetism isn't a footnote. It's the weather. Jupiter has a magnetic field so powerful it would dwarf a refrigerator magnet by a factor of millions. It stretches far beyond the orbits of its major moons, sweeping past them as Jupiter rotates every 10 hours. as that giant magnetic field sweeps past Europa, it doesn't just glide politely. It cuts through the moon like a changing electric tide. And if there's anything electrically conductive inside Europa, those changing fields will drive currents, which in turn create their own magnetic field. So Galileo flew past, over and over, and the magnetometer listened. It measured the background field from Jupiter, and then it watched how that field was distorted in Europa's neighborhood. The signature it saw around Europa wasn't steady, like you'd expect from a permanent, iron core-style magnetic field locked to the moon. It shifted in a very particular way as Europa moved through Jupiter's tilted magnetic field, as if something inside was being forced to respond, lagging just a bit behind the external change. That pattern is the giveaway. An induced field, not a bar magnet frozen into rock, but a magnetic echo generated by electrical currents in a global conductor wrapped around the moon. What kind of conductor fits a spherical shell, buried beneath ice and strong enough to match Galileo's data? A salty ocean. Not a local lake, not a pocket, but a worldwide layer of briny, electrically conductive water hidden under the crust. We still didn't see the ocean. We saw its magnetic shadow, a whisper in the data that said, very clearly, something liquid and salty is down here, and yet something is above the planets. Something is below them. In Europa's case, the ice is the visible skin. The real world is the unseen layer below, announcing itself only through gravity and magnetism. So, let's start at the very beginning of how you probe a hidden ocean after that first whisper. If you can't dive through kilometers of ice, how else do you weigh, map, and test an ocean you can't see? So if you can't drill, you do the next best thing. You throw a robot past Europa at several kilometers per second and watch how its speed twitches in the grip of invisible mass. That's what Galileo did in the 1990s, and what Europa Clipper will do with far more precision. As the spacecraft flies by, Europa's gravity ever so slightly bends its path and tugs on its velocity. By tracking the radio signal from Earth, we can see those tiny shifts in frequency and timing. Because here's what nobody tells you. That wobble in the signal is a seismograph for the entire moon, written in units of speed and pulled by gravity alone. From those flybys, you can build a picture of how mass is stacked inside. Dense rock and metal pull harder. Low-density layers pull less. When scientists did the math, Europa's overall density came out too low for a solid rock world, but too high for a pure ice snowball. The only way to make the numbers behave is to add a thick layer of water, sandwiched between a rocky mantle below and an icy shell above. You know the one, the ocean we keep talking about but still haven't seen. And yet, something is above the planets. Something is below them. In Europa's case, that below isn't just rock. The gravity field hints at a global ocean, tens to maybe hundreds of kilometers deep, with more water than all of Earth's oceans combined. A solid Europa would transmit Jupiter's pull like a single rigid bead in orbit. But a Europa with a liquid layer, that's a bead with a sliding skin. This is where tidal love numbers come in, with a name that sounds way more romantic than the equations deserve. They measure how much Europa's shape flexes as it orbits Jupiter, swelling a little along the line of gravity and relaxing as it swings around. If the interior were fully solid, that tidal bulge would be small and stiff. Add a decoupled ice shell floating on liquid, and the bulge gets larger, the response more squishy. So when we measure Europa's tidal wobble, it's bigger than a solid body should allow. The love numbers say that ice is riding on something that can flow, slipping over a global ocean instead of being welded to the rock below. Between the induced magnetic field and this tidal flexing, the case for an ocean looks almost airtight. But what kind of ocean is it? Is it fresh, salty, acidic, alkaline, rich in chemistry, or barren as melted snow? Now let's begin to ask the question that really matters. Could that hidden sea actually support life? So if we can't dive into that ocean yet, we do the next best thing. We read the scars on the lid. Europa's surface looks smooth from far away, but when you zoom in, it's a battlefield. Huge regions called chaos terrains look like someone took the ice shell, shattered it into city-sized plates, stirred them, and then froze the mess in place. You see tilted blocks, rotated rafts, dark gaps filled with refrozen slush. Because here's what nobody tells you. That kind of jumbled geometry is exactly what you get when solid ice is disrupted over something that can move. On Earth, you see a similar picture where sea ice breaks up over swirling currents. Plates drift, collide, overturn, and then lock back together when the temperature drops. On Europa, we think those chaos blocks may have detached, bobbed around on a layer of warmer, softer ice, or even on pockets of liquid, before freezing back into a frozen traffic jam. It's not just broken for the sake of being broken. It's broken in a way that hints at buoyancy, at upwelling, at motion from below. Then there are the double ridges and lineae, long, parallel cracks and raised rails that crisscross the moon like someone scribbled with a planetary scale pen. Some of these ridges are hundreds or thousands of kilometers long, yet only a few hundred meters high. They look simple in a flat picture. They're not. The best models say they form when fractures open and close over and over as Europa flexes in Jupiter's gravity, pumping water or slush up and down like a piston. So, let's start at the very beginning of that process. Tidal forces bend the ice shell. Fractures open, letting fluid rise and freeze. Then the shell relaxes and clamps shut, squeezing the new ice into a ridge. Repeat this cycle for millions of orbits, and you build a landscape of frozen heartbeats, each ridge a seismograph line of the ocean's mechanical coupling to the shell. And yet, something is above the planets. Something is below them. In the same way, something is above Europa's ocean, and below its vacuum sky, this restless, scarred ice. When we compare Europa's ridges and chaos to Earth's polar sea ice, the resemblance is unsettling. It's as if the moon is behaving like a miniature ocean world, pressed into a thin, brittle crust. The ice is not just sitting there. It's listening to the ocean, and it's answering. Some regions look almost fresh, with fewer impact craters than you'd expect over billions of years. That means resurfacing. Old terrain erased, new ice laid down. To keep rewriting the surface, Europa needs internal heat and mobility, the kind you get from tidal flexing of a deep, global ocean. Pattern interrupt. Europa's surface is not a static, frozen lid. It's a dynamic interface, a living fault line where the hidden sea keeps trying to write messages in fractures and jumbled plates. The trick for us is learning how to read them well enough to predict what that ocean is really like, and whether something alive is down there, pushing back. Now that we've read the scars, we can finally ask, how thick is this lid? And why does that thickness make the ocean so much harder to know than the ice we can see? That lid isn't just cold ice. It's an active chemical skin being sandblasted by Jupiter every second. Europa lives deep inside Jupiter's radiation belts, where charged particles spiral along magnetic field lines and slam into the surface at incredible speeds. They shred water molecules, kick oxygen out of the ice and rearrange atoms into new compounds right in the top millimeter or so. In space, there is no up, there is no down. But there is a brutal above where radiation rules, and a quiet below where the ocean hides. Because here's what nobody tells you. When you look at Europa's bright, almost flat white plains and its rusty fractures, you're not seeing pristine ice. You're seeing a crime scene that's been tampered with. The original molecules have been broken, swapped, and stitched back together under a constant hail of electrons and ions from Jupiter's magnetic orbit. So how do we know what's really there? We split the light. When sunlight hits Europa and bounces back, it carries a spectral barcode. With spectroscopy, we can read that barcode and pick out the fingerprints of different materials. Water ice dominates, sure, but it's not alone. We see signs of hydrated salts and weird darkening agents that don't match pure ice. Some regions, especially along the long cracks and those younger, chaotic terrains, show signatures that may include magnesium or sodium salts, and even something like sulfuric acid. You know the one. That reddish-brown staining along the lineae that makes Europa look like it's been scored with a rusted knife. Those colors are a clue. One idea is that salty water from the subsurface ocean is forced up through fractures, freezes on the surface, and then gets cooked by radiation into darker compounds. The salts start out looking relatively clean, but under Jupiter's particle storm, they morph into the strange hues we see in the telescope picture. Now let's begin to see the real problem. If radiation is constantly rewriting the surface, how do we tell which ingredients were delivered from below and which were manufactured right there in the ice? Are those salts a direct sample of the ocean, or are we mostly seeing a chemistry experiment powered by Jupiter's radiation belts? Every spectrum we take is a mixture of ocean memory and surface processing, and untangling the two is like trying to reconstruct a message after it's been run through a noisy, glitchy filter. And yet, something is above the planets. Something is below them. Europa's skin is noisy, but it might still be speaking for the ocean. So the next question is brutal and simple. If this surface is a distorted message, is there any way to catch the ocean speaking more directly? So if the surface is a garbled message, is there any point where the ocean just shouts? For a while, it looked like the answer was yes. Back in the 2010s, the Hubble Space Telescope stared at Europa as it crossed in front of Jupiter and caught something strange. Faint fingers of extra absorption near the South Pole, as if wisps of water vapor were silhouetted against the giant planet. You know the one. The headline that followed was irresistible. Europa might have geysers, just like Saturn's moon Enceladus. That comparison matters. At Enceladus, we've literally flown a spacecraft through towering curtains of ice and vapor blasting out of its south pole, tasting salts and organics that almost certainly come from a subsurface ocean. If Europa is doing anything even remotely similar, those plumes would be the closest thing we have to the ocean, punching a hole straight through the ice and breathing into space. Because here's what nobody tells you. If even a small fraction of that vapor comes from the global ocean, and not just a shallow pocket, then every plume is a free sample return mission. No drills. No landers melting down for decades. Just open your instruments and let Europa's gravity do the delivery. Of course, that's the dream. The reality is messier. After those first Hubble hints, follow-up observations were inconsistent. Sometimes, with careful image processing, you see what looks like a column of vapor tens or hundreds of kilometers high. Other times, looking at the same regions, the signal vanishes. No plume. Just the usual thin oxygen atmosphere hugging the ice. So what's going on? Are the plumes tiny, rare, or both? Are we chasing statistical noise and wishful thinking? Or are we catching a real process that only turns on under particular tides, particular fractures, particular alignments we haven't fully mapped yet? In a way, we're right back to our flat solar system diagrams. The first picture was clean and simple, and the truth is turning out to be much more chaotic in 3 dimensions. Now let's begin the part where we stop just watching from Earth and actually go there. NASA's Europa Clipper will sweep past Europa dozens of times, threading low orbits through regions where Hubble saw those hints. On board are mass spectrometers designed to sniff individual molecules in the whisper-thin gas around the Moon, plus dust analyzers that can catch tiny ice grains. If Clipper flies through even a modest plume, it can weigh water molecules, measure salts, detect organics, and look for patterns that scream ocean chemistry instead of random surface frost. In the absolute best case, we'd see combinations of molecules that are hard to produce without active hydrothermal vents or ongoing water-rock reactions. That wouldn't prove biology, but it would turn the volume way up on the habitable ocean side of the argument. And yet, something is above the planets. Something is below them. If Europa's ocean refuses to vent, if plumes are vanishingly rare or don't exist at all, then we lose that direct breath into space and fall back on magnetic whispers and frozen scars. So how do you design missions and instruments for an ocean you might never, ever touch? So here's the strange twist. On Europa, the part that could actually be alive is the part we can't really see, while the dead, frozen skin is the part that talks to us all the time. The ice is an open book because our tools were built for exactly this kind of problem. Cameras, spectrometers, thermal imagers, they love surfaces. You fly a spacecraft past Europa, you point the instruments down, and the photons just pour in. You get that bright, almost blinding ice with an albedo around 2/3. You get the rust-colored streaks. You get temperature maps that show where the shell is leaking heat. It's like reading a page under a spotlight. The ocean, that's a locked vault. Light never reaches it. Our cameras see nothing. So we're forced to listen sideways, through gravity and magnetism, and if we're lucky, radar echoes that have slogged through tens of kilometers of ice. Galileo's magnetometer picked up an induced magnetic field, which is strong evidence for a global salty ocean. But notice what that actually is. It's not a picture of waves and currents. It's a wiggle in a graph that you only understand after you subtract Jupiter's main field, model Europa's orbit, and assume a range of conductivities. Because here's what nobody tells you. For the ocean, almost every image is really a simulation dressed up as a map. Accessibility is the other brutal difference. We can fly right past the surface, skim a few hundred kilometers above it, map every ridge and chaos terrain in high resolution, even dream about landing. The ice is in the same kind of geometric situation as the planets in that flat solar system picture. It lies on the outside, in the plane of our instruments. But to reach the ocean, you're talking about drilling through a shell that might be 5 kilometers thick or 30. Both numbers fit the data. Both numbers completely change how you'd ever try to get through. And the signals themselves? The ice shouts, cracks, bands, frozen rafts of broken crust, all high contrast, visually obvious scars. Something shifts in the tidal stress. The ice fractures, and within geologic moments you have a new feature You can literally photograph from across space. The ocean whispers. Its response to tides and heat is smoothed out, buffered by depth and pressure. So what reaches our instruments is a faint change in gravity here, a slight tweak in the induced field there. You know the one, the kind of signal where 3 different teams publish 3 different interpretations. So here's the pattern interrupt. We love to call Europa an ocean world with ice on top. But from our vantage point, it's really an ice world with a ghost ocean implied beneath it. The shell is mapped, the water is inferred, and yet something is above the planets. Something is below them. In the same way, something is above Europa's ocean, and something is below it. And right now, the part below is still more rumor than landscape. Now let's begin to ask a harder question. If the vault stays locked, how far can we really push these indirect tricks before we fool ourselves about what's swimming in the dark? So here's the uncomfortable part. When we say Europa has an ocean, we usually skip the follow-up question that actually decides everything. How much ice is in the way? Because here's what nobody tells you. That number is wildly uncertain. Depending on which model you believe, Europa's ice shell could be as thin as about 5 to 10 kilometers, or as thick as 20 to 30 kilometers or more. That's the difference between dig through a mountain and dig through a small tectonic plate. For mission planners, that isn't a detail. That's the whole game. So, let's start at the very beginning of this argument. You look at Europa's surface geology, and one picture jumps out. Chaos terrains, broken plates of ice that look like they've been floated, rotated, and refrozen. If you squint, it's like watching sea ice on Earth fracture over the liquid water. That kind of behavior screams thin, mobile shell, the 5 to 10 kilometer team. In that world, the ice flexes easily, cracks open, and lets ocean material leak upward. But then you ask how Europa responds to Jupiter's gravity as it orbits, and the story can flip. Tidal models, where you watch how much the moon should bulge and flex, can be tuned to support a thicker, more rigid shell, 20 to 30 kilometers or beyond. Thermal models join in. If the ice is too thin, it might melt through too quickly. Too thick, and it locks up, turning Europa into more of a frozen tomb. The same data points, surface fractures, heat flow, even tiny changes in Europa's orbit can be made to fit either camp with just a few different assumptions. Now, why does this thickness obsession matter so much? Because a thin shell means the surface and the ocean are in constant conversation. Cracks can punch all the way down. Brines can percolate all the way up. Radiation on the surface can create oxidants and other chemicals that get dragged into the ocean, feeding possible ecosystems. If life exists down there, some of its biosignatures might ride that conveyor belt back toward the vacuum of space where we can sniff them. Push the shell out to 20 or 30 kilometers, and the whole mood changes. The ice turns into a serious insulator, a barrier that isolates the ocean from the surface for long stretches of time. Venting becomes rarer, smaller, more localized. The surface we can see turns into a distorted, delayed reflection of what's happening below, like trying to infer a stormy sea from a concrete ceiling. And yet something is above the planets. Something is below them. The same is true here. Above the ocean lies an ice world we can photograph. Below it, a hidden sea we can only model. This single unknown, how thick that ice really is, controls how reachable the ocean is, how often it might vent, and how honestly the surface reports on the abyss. Now let's begin to bring in a new kind of scenes. future missions that will literally fire radio waves into the ice and listen for echoes from the dark, turning Europa's shell into a three-dimensional map instead of a blank white wall. We're about to give the ice X-ray vision, not by drilling, not by melting, but by teaching a spacecraft to listen for whispers that bounce around inside a frozen shell. So, let's start at the very beginning. On Earth, if you want to know what's hiding inside a glacier, you don't just stare at the surface and hope. You fire radio waves into the ice. Those waves dive down, hit boundaries between different layers, and some of the energy echoes back. By timing those echoes, we can map internal layers, buried lakes in Antarctica, even the bedrock under the Greenland ice sheet. It's ultrasound for ice, except the sound is radio. Europa Clipper is bringing that trick to Jupiter's realm. Tucked on board is an ice-penetrating radar designed to punch through kilometers of European ice. Every time the spacecraft sweeps past, it will send sharp pulses down through the shell, then listen as they bounce off anything that changes the ice's properties. A shift from fluffy, fractured ice to denser ice. A pocket of salty brine, maybe even the top of the global ocean itself. Because here's what nobody tells you. If there really is a vast liquid ocean down there, the top of that ocean should be a spectacular mirror for radio waves. Ice above, liquid below, a clean change in density and composition. In principle, that boundary should light up in the data as a bright, flat reflector, the same way the base of an Antarctic ice sheet jumps out in radar profiles back home. But radar is powerful in a very particular way. It can reveal layering. It can hint at pockets of slush and brine. It can give us an approximate ice thickness and show where the shell is thick, where it's thin, where it's broken. What it cannot do is give you a postcard of Europa's ocean. No shimmering waves, no alien fish silhouettes, no high-definition picture of the seafloor. At best, we see the ghost of a surface, a line in a graph that says, "Here, liquid starts here." And Europa will not make this easy. Jupiter's brutal radiation will hiss in the antennas, trying to drown out the echoes. The ice itself is probably a chaotic mix of pure water, ice, salty veins, refrozen fractures, and rubble, each twisting and scattering the signal. We don't even know the exact electrical properties of that ice under European conditions, which means every radar trace will come with a question mark. Is that a real boundary, or just a trick of the medium? So what do we really gain? We sharpen the outline of the shell. We turn that single unknown, how thick is the ice, into a detailed, three-dimensional picture of layers, fractures, and if we're lucky, the bright flat base where solid gives way to liquid. And yet something is above the planets. Something is below them. In the same way, something hard will sit above something liquid on Europa, and radar will let us sense that divide without ever touching it. The ocean itself will still be a rumor, detected as a reflective boundary rather than a direct view. A ghost line under the ice, so in the next part, we'll push even further into the indirect. How Europa's invisible ocean tugs on gravity and magnetic fields, and how those invisible forces let us weigh and salt test a sea we cannot see. So if the ocean is a ghost line under the ice, who do we send to go ghost hunting? Now let's begin with the two machines that are about to haunt Jupiter's system in the best possible way. NASA's Europa Clipper and ESA's JUICE mission. They're not rivals. They're a tag team. Clipper will swoop through the Jovian system in a long, looping orbit, performing dozens of close flybys of Europa. JUICE will tour the neighborhood too, focusing more on Ganymede and Callisto, but still swinging past Europa to grab crucial passes. You know the one. That classic flat diagram with tiny spacecraft icons tracing neat paths? In reality, these trajectories are three-dimensional spirals, bent by gravity, radiation, and fuel budgets. Because here's what nobody tells you. When you can't touch the ocean, you have to turn the space around it into your laboratory. So both missions are absolutely packed with instruments designed to read fields and surfaces instead of waves and currents. Clipper and Juice will carry ultra-sensitive magnetometers to refine Galileo's measurements of Europa's induced magnetic field, gravity science experiments that track tiny tugs on the spacecraft's orbit, ice-penetrating radar to map internal layers, thermal imagers to sniff out warm spots, and spectrometers to decode the chemistry painted across that bright, scarred ice. None of this drills a single centimeter into the shell. No robot submarines. No sample tubes dipped into a European tide pool. These missions are built around a hard constraint. Jupiter's radiation makes long surface operations brutal, so you fly past fast and high, and you squeeze every bit of information out of the brief windows you get. It's like trying to understand an entire ocean by reading ripples on a frozen lake from a passing airplane. That's why mission designers obsess over flyby geometry. How close can we skim the surface before radiation fries our electronics? Which angles give the magnetometer the cleanest view of the induced field? Or let the radar beam hit the ice at just the right incidence to see the ocean boundary? Every pass is a trade. A lower altitude might sharpen gravity measurements but shorten instrument lifetimes. A different trajectory might favor Juice's view of Ganymede while giving Clipper a better shot at Europa's equator. And yet, something is above the planets. Something is below them. In this case, what's above Europa's ocean is a hostile radiation bath. What's below it is a rocky mantle we can only wave from afar. Even with all this hardware, there is a ceiling to what orbiters can tell us. So the question hangs there, just under the ice. Once we've pushed flybys and remote sensing to their limits, do we dare send something to land on that glassy plain? Or even dive into the hidden sea beneath it? Or even dive into the hidden sea beneath it. Here's the twist. The hardest question about Europa's ocean isn't, can we get in? It's, are we even allowed to try? Because the moment you stop thinking like an engineer and start thinking like a biologist, the whole mission plan tilts on its side. Planetary protection sounds like a sci-fi security protocol, but it's real. It's international. And it hangs over Europa like invisible police tape. Space agencies have agreed that worlds which might host life sit in a special category. You don't get to just drop hardware there, scrape some ice, and call it a day. You have to prove that you won't smear Earth microbes across a place that could hold the first alien ecosystem we ever find. Because here's what nobody tells you. Our planet sheds life the way a cloud sheds rain. Your skin, your breath, the clean room where a spacecraft is assembled, even the alcohol-wiped metal surfaces. They're all battlegrounds where microbes cling on. Some of them are annoyingly good at surviving. We found bacteria that shrug at vacuum, endure brutal cold, and ride radiation doses that would turn you into a cautionary tale. So, when we say we'll sterilize the probe, what we really mean is we'll wage war on life and hope we win by enough. Heat, chemicals, radiation, meticulous assembly and filtered air. All of that just to reduce the odds that a single spore hitches a ride to Jupiter's neighborhood. And yet, something is above the planets. Something is below them. Europa sits out there in the outer solar system as a test of whether we can keep our biological footprint inside our own orbit. Now imagine the nightmare version of the story. We finally build a lander that can melt or drill through kilometers of ice. It reaches the ocean, samples the water, and finds life, cells, metabolism, weird but familiar chemistry. The headlines scream, "Alien microbes discovered." And then 10 years later, genomic analysis whispers a darker punchline. Those organisms are just slightly mutated Earth bacteria we unknowingly delivered decades earlier. In one move, we would have erased Europa's pristine record and permanently confused the picture of what life can be in space. Was there ever native biology down there? Did we overwrite it? Did we outcompete it? Those are questions we could never truly untangle. So let's start at the very beginning of the engineering problem. You need a machine that can survive Jupiter's radiation bath, thread through that gravity well, land on a fractured, jagged ice plane, then punch through a shell that might be 5 kilometers thick or 30, all while staying cleaner than an operating room for years without a human ever touching it again. At this point, the pattern interrupt hits. We stop asking, how deep can we drill? And start asking, should we drill at all? Do we treat Europa's ocean like a protected wilderness we only study from above? Or do we accept the risk of touching it, knowing we might never be able to take that touch back? In the next part, we'll look at the compromises scientists are quietly designing to walk that razor-thin line. So if we're walking that razor-thin line and decide we won't punch through the ice, what then? If we never send a drill, never drop a submarine, what would it actually take for scientists to look at Europa from orbit and say, out loud, that's life? Not interesting chemistry, not could be. Life. Because here's what nobody tells you. Most of the time, life doesn't announce itself with fossils or tentacles. It whispers in ratios, in combinations of chemicals that shouldn't sit together in the same place for very long unless something is constantly pushing them out of balance. On Earth, our atmosphere is wildly out of chemical equilibrium because biology keeps it that way. Oxygen and methane coexist in a way that geology alone has a hard time sustaining. So, let's start at the very beginning of what we could look for on Europa without ever touching the ocean. Imagine a spacecraft flying through a thin cloud of material above the ice, sampling individual molecules like snowflakes in slow motion. If Europa does have plumes, geyser like jets blasting ocean water through cracks and into space, then the ocean is literally leaking into the vacuum where our instruments are most comfortable. You know the one. The classic picture of a probe flying through Enceladus's plumes at Saturn, tasting salts and organics. We want that same move at Jupiter. A Europa orbiter could fly through a plume and sniff for complex organic molecules, long carbon chains, amino acids, or strange combinations of oxidants and reductants, things like hydrogen peroxide and molecular hydrogen that together represent chemical batteries. If we saw those batteries repeatedly, half drained, in a way that matches how microbes on Earth eat, that would make a lot of people sit up very straight. We'd also be watching the surface. Radiation from Jupiter is constantly hammering Europa's ice, remixing the top few millimeters. If the ocean slowly cycles material upward, then patches of ice above active regions might show weirdly fresh chemistry, too much of certain organics, or patterns of sulfur and carbon that don't line up with simple inorganic reactions. Even the exact mix of salts, magnesium versus sodium, chlorides versus sulfates, could hint at metabolisms operating far below the plane of the visible surface. But here's the catch. Almost every chemical signature you can dream up has a non-biological explanation. Abiotic processes can make organics. They can separate oxidants and reductants. They can sculpt gradients that look, from a distance, suspiciously alive. In a world we've never seen directly, how do you prove what you can't touch? And yet, something is above the planets. Something is below them. Europa's ocean might host a biosphere whose fingerprints don't look like ours at all. What if its life never learned to breathe the way we do? Never built the kinds of molecules we're trained to recognize? We could fly through its plumes, map its ice, listen to its gravity and magnetic field, and still miss the signal because we were staring at the wrong picture of what life is supposed to be. In the next part, we'll push that unsettling idea even further and ask, what if Europa is alive, but not in a way our instruments, better Frank, or our imagination are currently built to see? So if Europa can hide an entire ocean from us, you might ask, do any ocean worlds actually cooperate? Do any of them just vent their secrets straight into space where we can fly through them? They do, but not at Jupiter. Now let's begin with Saturn's tiny troublemaker, Enceladus. You know the one, a moon so small you could fit it inside the Mediterranean, and yet at its south pole it behaves like a broken fire hydrant in space. Great plumes of water vapor and ice grains blast out through long fractures nicknamed tiger stripes, spraying material from a subsurface ocean directly into Saturn's orbit. Because here's what nobody tells you. For Enceladus, the ocean is already in space. You don't have to drill. You don't have to melt. You just fly a spacecraft through the plume and let the moon do the hard work. That's exactly what Cassini did. It threaded those geysers multiple times, using its instruments like open mouths, sampling salts, organic molecules, and tiny grains that had frozen mid-flight. Cassini could measure the chemistry of an alien sea without ever seeing the sea. Salts told us the water was in contact with rock. Organics hinted that complex carbon chemistry was underway. The plume itself became a liquid biopsy of the interior, a direct line from ocean floor to detector. For a world 1.4 billion kilometers away, that feels almost intimate. Now put that picture next to Europa. Same basic idea on paper. Icy shell, global ocean, rocky mantle, possible hydrothermal vents. But when we look for Europa's version of those showy plumes, the story gets murky fast. Hubble has seen hints of something venting off Europa's limb, but those signals are faint, sporadic, and hard to confirm. Europa Clipper will go hunting for them, but right now, we don't have a roaring South Polar geyser field to treat like a cosmic car wash. We have suggestions. Maybe weak, maybe rare, maybe angled so that flying through them safely in Jupiter's radiation is a nightmare. So instead of scooping ocean particles out of space, we're reading indirect clues, an induced magnetic field that whispers salty liquid, gravity measurements that hint at a decoupled shell, radar reflections that sketch the ice but not the waves beneath it. Enceladus feels open, Europa feels sealed, and Jupiter's environment slams that door even harder. Radiation near Europa is brutal. Spacecraft can't just loiter in low orbit, dipping again and again through hypothetical vents like Cassini did at Enceladus. Every close pass is a calculated risk. The result is that Europa's ocean isn't only physically hidden by kilometers of ice. Compared to Enceladus, it's observationally distant, even ethically distant. Do we really want to crash through a fragile environment? with a lander if we don't yet understand the only access points. And yet something is above the planets. Something is below them. One ocean we can taste from orbit. One we can only infer from fields and fractures. In the next part, we'll ask what it means to explore a world like Europa responsibly, when the easiest path to certainty might also be the most intrusive. So if the ice is our doorway and the ocean is the hallway, what's at the very end of that corridor? The place Europa is really hiding from us is not the water at all. It's the rock. Now let's begin at the bottom of this world, beneath that global ocean, beneath hundreds of kilometers of liquid and slush. Models say Europa has a rocky mantle and very likely a metallic core, compressed and differentiated by gravity, just like Earth's interior. Picture a miniature Earth turned inside out, iron and nickel in the middle, hot silicate rock around that, then an enormous dark sea, then the frozen shell we can actually see. Because here's what nobody tells you. For life as we know it, the water alone isn't enough. You need water meeting rock. On Earth, some of the most vibrant ecosystems we've ever found live where the ocean floor cracks open at hydrothermal vents. No sunlight, no photosynthesis, just chemical gradients where hot mineral-rich fluids gush into cold seawater and microbes use that chemistry as fuel. You know the classic picture of black smokers belching out dark plumes while weird pale creatures cluster around them like it's a deep-sea campfire. If Europa is alive, that's the kind of party we're looking for. And there are good reasons to think the seafloor might be active. Tidal forces from Jupiter don't just need the ice. They flex the rocky interior, generating heat. Add in the slow burn of radioactive decay in the mantle, and you have a recipe for warm spots, fractures, and maybe full-blown hydrothermal systems on the ocean floor. Some models even predict long-lived vent fields, continuously pumping chemical energy into that dark water. In other words, the most promising real estate for a European biosphere might be pinned to the rock, not drifting in the middle of the ocean. But here's the catch. That rock-water interface is the most hidden part of an already hidden ocean. We can map Europa's ice fractures from telescopes. We can infer an ocean from its induced magnetic field and from how the moon's gravity tugs on a spacecraft's orbit. The seafloor? Nothing. No direct measurements of its topography. No confirmation of vents. No sample of its minerals. For all our beautiful data, the actual habitat we care about most is still a blank page. And yet, something is above the planets. Something is below them. Used to thinking of oceans as surfaces, as flat blue plains on a map, Europa forces us to flip that picture and ask a stranger question. If the crucial layer for life is buried under ice, underwater, and under rock, how do we even start to reason about a biosphere we cannot see, touch, or image? In the next part, we'll try to build that invisible ecosystem from physics alone and see where the cracks in our confidence start to show. So if we can't see the ocean, how do we do science on it at all? You're not going to park a submarine under tens of kilometers of ice next year. So we cheat. We swap metal and propellers for math and processors. Now let's begin with the basic move. In place of submarines, we have equations, fluid dynamics to tell us how water flows, thermodynamics to track how heat seeps, convects and erupts, chemistry models to follow ions and minerals as they drift, react, and settle. On Europa, those equations become our only way to watch an invisible sea circulate, overturn, and evolve over billions of years. Because here's what nobody tells you. You can't just simulate a random ocean and call it Europa. You have to bolt your virtual ocean to hard constraints. We know Europa's size, its mass, its gravity. We know how fast it spins, how it orbits Jupiter, how that orbit gets flexed by the other big moons. Feed all of that into a model. Add the tidal heating pattern inside the rocky mantle, and the computer starts to predict where the water should be warm, where it should be cold, and how it might move between those regions. You end up with temperature gradients that look like weather maps, but turned sideways. Hotter layers near the seafloor, cooler ones pressed against the ice. Jets and gyres that could shuttle nutrients from bottom to top. In some simulations, heat focuses into narrow plumes, punching up against the ice like slow-motion geysers. In others, the whole ocean turns over so lazily that a molecule could spend centuries drifting in the dark before ever meeting the roof. Then the chemists get their turn. They simulate how salts dissolve from the rocky seafloor mix with oxidants created at the irradiated surface and drag down through cracks. They track magnesium, sodium, sulfates, maybe even traces of organics, swirling in 3D under Europa's gravity. The question is simple but brutal. Do those ingredients arrange themselves into energy gradients that life could actually use? Or do they smear out into a bland, uniform soup? And yet, something is above the planets. Something is below them. On Europa, that symmetry becomes. We can sketch the ice as if it were a flat map, but the ocean beneath only exists, in detail, inside code. Pattern interrupt. Right now, the most complete maps of Europa's ocean are not in a spacecraft memory. They live on supercomputers in places like Pasadena and Berlin. Change the assumed ice thickness by a few kilometers, and the circulation can flip from vigorous to stagnant. Tweak the tidal heating, and hydrothermal vents either light up the seafloor or barely glow. Adjust the salt content, and the ocean's density structure and its habitability shifts. So, let's start at the very beginning of our humility. Tiny changes in input create entirely different alien climates, which means before we ever drill, we're already arguing over multiple Europas. The next step is to see which of those digital oceans survives contact with real data. But there's one layer of Europa that doesn't wait for us to drill or dive or simulate. It's already reaching out into space. It's the part of Europa that actually touches the vacuum you and I imagine when we picture the solar system. Above the ice, Europa wears a ghost, a whisper-thin atmosphere, so tenuous you'd barely dignify it with the word air. If you stood on the surface with no suit, you wouldn't feel wind on your face. You'd barely have enough molecules to call it a breeze. And yet, this almost nothing is mostly oxygen. Because here's what nobody tells you. Europa's oxygen doesn't come from forests or oceans or anything alive. It comes from violence. Jupiter's radiation slams into the ice, splits water molecules into hydrogen and oxygen, and the light hydrogen escapes Europa's weak gravity, while the heavier oxygen lingers, hovering in a fragile exosphere that's more like a slow-motion leak than an atmosphere. Now let's begin to appreciate the irony. That nearly non-existent exosphere, we can measure it directly from worlds away. Instruments watch Europa pass in front of Jupiter or stars and see which wavelengths of light get nibbled away by oxygen. Ultraviolet, infrared, the spectral fingerprints tell us how much is there, how it glows, how it changes as Europa orbits in and out of Jupiter's magnetic fury. You know the one, the flat textbook picture where Europa is just another moon dot in Jupiter's orbit. In that picture, you never see the invisible belts of charged particles wrapped around Jupiter like a deadly halo. But those radiation belts are real, and Europa plows through them every day. On the surface, they deliver doses that would fry unprotected electronics in hours and make a human mission feel less like exploration and more like slow X-raying. That radiation doesn't just threaten landers, it rewrites the surface. It bakes new chemistry into the ice, shuffles atoms, forges oxidants that might, over geologic time, trickle down through fractures toward the ocean. So the very thing that makes Europa's surface hostile could also be feeding its hidden sea with chemical energy. That's a brutal kind of generosity, but it's the kind space specializes in. And here's the twist. Because this atmosphere and this radiation environment interact with space, we can characterize them in absurd detail. We watch charged particles stream past, map how Europa's exosphere brightens and dims, even estimate how fast ice is being sputtered off into a faint global cloud. The topmost skin of Europa's environment is, in a sense, the part we know best. And yet, something is above the planets. Something is below them. Above Europa's ice, we can read every ghostly interaction with light and gravity. Below the ice, the ocean that might hold more water than all Earth's seas combined stays silent. So what does it really mean to say that ocean is below the ice, in a place where up and down are just choices we make on a flat diagram? On Europa, below the ice sounds obvious. You picture a ceiling of frozen white and an ocean hanging underneath, like water in a basement. But in space, that intuition starts to wobble, because here's what nobody tells you. Europa doesn't come with pre-installed directions. We bring those with us. Physically, down on Europa just means one thing: toward the center of mass, toward where gravity is pulling you. Up is away from that center, out into space. That's it. No cosmic arrow painted on the ice, no universal label that says, this way is north. Everything beyond that is a convention we agree on, so we can talk about the same picture without getting lost. So, let's start at the very beginning of how we tame a spinning, orbiting ice world. Europa is locked in synchronous rotation with Jupiter, always showing the same face to the planet. Astronomers take that rotation and its orbit, define an axis, and declare one end north and the other south. You know the one. Neat globes in textbooks with tidy latitude and longitude lines. It works beautifully for maps and for spacecraft navigation. But Europa itself doesn't care. If you flip the labels overnight, the moon would not notice at all. When we say the ocean is below the ice, what we really mean is that it sits deeper in Europa's gravitational well, wrapped closer to the center, hidden behind a physical barrier of tens of kilometers of ice. It's not lower in any metaphysical sense, it's just more shielded. The ice shell is the part that talks to sunlight and to Jupiter's radiation. The ocean is the part that talks to gravity and magnetism. So whose point of view are you using when you decide which one is above? Spacecraft have to pick an answer. Europa Clipper will fly past this world along carefully calculated trajectories that are defined in a coordinate system. X, Y, Z axes tied to the Europa's rotation and orbit. Its instruments have fields of view that point nadir, toward the center, zenith, away from it, or off to one side. A radar pulse that looks down through the ice is only down because we agreed that the vector toward the center is negative z. Change the sign, and suddenly your radar is looking up into the same ice. Even our diagrams trap us. We draw cross-sections with the surface as a flat line at the top of the page, the ocean as a blue band underneath, the rocky mantle and metallic core stacked below that. It feels natural. It's also a choice. Rotate the whole diagram 90 degrees and nothing physical changes. The ocean doesn't slosh sideways because you turned the paper. Now let's begin to stretch that idea. If surface and interior are this flexible on a 3,100 kilometer wide moon, what happens when we zoom out? What does it even mean to talk about the inside of a galaxy or the edge of the solar system, when every up and down is just a reference plane we've decided to honor? So here's where our brains quietly betray us. We hear interior, edge, inside, and we still picture a surface, a boundary you could, in principle, walk up to and tap with your knuckles. Because here's what nobody tells you. Human perception is tuned for skins, not depths. You evolved to read bark, not x-ray a tree. If you can see the outside of a thing, a rock, a book, a planet, you instinctively feel like you've got the object mostly handled. The visible layer feels like a summary. Europa plays right into that bias. We have razor-sharp images of its ice, every crack and ridge lit by the sun, albedo so high it almost glows. We can map chaos terrains, count impact craters, measure how bright or dark different patches are. You look at those photos and your brain does something sneaky. It quietly promotes surface to world. You feel like you've met Europa, but that is a trick of the picture, not the physics. Those diagrams with neat cross-sections, thin atmosphere, ice shell, blue ocean, rocky mantle, metallic core, look complete, like a textbook cutaway of a machine. You know the one. A perfect circle sliced open, every layer colored, every boundary sharp. It feels like a confession from the moon itself. In reality, almost everything below that ice is an inference, not a photograph. Think about how absurd this would sound in daily life. Judging Earth's entire climate from one satellite snapshot of a sunny afternoon over your city, assuming you know the whole plot of a novel because you've seen a high-resolution image of the cover on a website. You can tell something, sure, but you're really just reading the paint on the outside. With Europa, we're doing the same thing, only at a planetary scale. We see the surface ice, so we feel like we see the ocean. The ocean leaves no direct image, only magnetic whispers in Galileo's data, tiny tugs in gravity measurements, chemical fingerprints in the ice that Jupiter's radiation has already scrambled. Estimates for the ice thickness range from about 5 to over 30 kilometers. That uncertainty alone means we don't even know how far away the ocean actually is. And this bias doesn't stop at the general public. Scientists have to fight it too. They build careful models of heat flow, of how salty water would respond to Jupiter's changing magnetic field, of how cracks might open if an ocean below is sloshing and freezing. Then they have to remind themselves, over and over, that the ocean and the seafloor are still constrained by theory and indirect data, not by any camera. So if our intuition is this easily hypnotized by a bright, icy skin, how do we build a mental model of Europa that keeps the hidden ocean front and center? How do we stop trusting the surface and start trusting the invisible signals written in gravity and magnetism instead? So to fix that, we need to redraw Europa in your head. Not as that neat, sliced layer cake you've seen in every textbook, but as something messier, fuzzier, and much more alive. You know the one. Perfect white shell, perfect blue ocean band, perfect rocky core, all divided by razor-sharp lines like a planetary wedding cake. It looks satisfying. It looks scientific. And because it looks so clean, your brain quietly decides, we basically understand this world. Because here's what nobody tells you. That diagram is more about our desire for order than about Europa itself. So, let's start at the very beginning of this new picture. Imagine Europa not as a flat cross-section, but as a thick, semi-transparent sphere hanging in space. The boundaries between layers aren't crisp. They're hazy zones, probability clouds where ice turns slushy, slush turns briny, and brine turns into true ocean. If you could fly around it with X-ray vision, you wouldn't see tidy stripes. You'd see gradients. Take the ice shell. In the old image, it's a uniform crust, same thickness everywhere, like the rind of an orange. In the real Europa, that rind is more like a patchwork quilt under stress. Some regions may have ice only a few kilometers thick, riddled with fractures and chaos terrain. Other regions may lock down under tens of kilometers of colder, stronger ice. Between them, layers of warmer, ductile ice can slowly flow, and pockets of salty brine might lurk like hidden lakes, feeding or draining those famous surface cracks. Now drop your eyes deeper into the ocean. Not a flat blue band hugging the rock in some polite, even layer, but a dark, three-dimensional volume, depth changing from place to place. Strong currents driven by Jupiter's gravity, by Europa's rotation, by heat leaking out of the interior, chemical gradients where fresh oxidants from the ice rain down in some regions, while other regions sit in long, energy-poor night. In one part of the ocean, the water could be only tens of kilometers deep. In another, it might plunge for over 100. And beneath that, the seafloor is the biggest blank of all. Mountains, plains, trenches, volcanic vents. Right now, they all exist only as competing models on a whiteboard. Wait, is Europa's rock rigid and quiet? Or is it cracked and venting like Earth's mid-ocean ridges? Does the core sit still or churn a metallic dynamo? We're guessing from gravity data and magnetic whispers. Pattern interrupt. If we were brutally honest, the most accurate diagram of Europa today would be a circle with blurry bands, big question marks, and error bars instead of lines. Not ocean at 100 kilometers, but ocean somewhere around here, depth highly uncertain. Not ice shell 20 kilometers, but ice shell 5 to 30 plus. Thickness varies. And yet something is above the planets. Something is below them. In the same way, something is above and below Europa's hidden ocean. But until we learn to think in probabilities instead of pretty slices, we'll keep underestimating how mysterious that interior really is. So how do we actually measure those fuzzy boundaries without ever drilling through the ice? That's where the next part of this story begins. Now let's begin by zooming out. Because here's what nobody tells you. Europa isn't a weird exception in the outer solar system. It's part of a whole family of worlds where the real action is buried under ice. Take Jupiter's other big moons. Ganymede, the heavyweight, likely hides a deep ocean sandwiched between thick ice layers, and it even has its own magnetic field. Callisto, way out in a calmer orbit, probably has a briny ocean too, hinted at by how its gravity field responds as it moves through Jupiter's magnetosphere. Shift to Saturn, and you meet Enceladus, spraying ocean material directly into space, and Titan, with lakes of methane on the surface and strong clues for a water ocean far below. Push farther still, and you reach Pluto and other distant dwarf planets, where fractured terrains and odd densities whisper that liquid water might still lurk in the dark. You start to see the pattern. Over and over, we infer oceans not because we see waves, but because gravity wobbles, magnetic fields twist, and the surface looks broken and resurfaced in very particular ways. The orbits tug on these worlds. They flex, they heat up, and that energy leaves fingerprints in the ice. In a flat diagram of the solar system, they're just tiny dots. In 3 dimensions, they're layered spheres, hiding global seas. And yet something is above the planets. Something is below them. The same is true here. Above these oceans, you have chaotic ice and thin atmospheres. Below them, you have rock and metal. What we actually measure are tiny changes in a spacecraft's path, subtle shifts in a magnetic field, strange young plains where old craters should be. From that, we reverse engineer a whole invisible ocean. So why does Europa stand out in this crowded family portrait? For one thing, it's bright. Its surface ice reflects sunlight so well that Europa becomes one of the most striking objects in any telescope, crisscrossed with rust-colored lines you can almost trace with your finger. That young, relatively uncratered skin screams, active world. Add in Galileo's measurements of an induced magnetic field, and you get strong evidence for a global salty ocean with more water than Earth has at the surface. All of this is happening deep inside Jupiter's intense radiation belts, in a region that constantly scrambles the chemistry of the ice we can see. So Europa sits in this strange sweet spot, one of the most promising places for life in the solar system and one of the hardest to study up close. Telescopes can map its cracks from Earth, but the ocean that might host biology is shielded by ice, distance, and radiation at the same time. It's a prime target and a uniquely frustrating one, and that leads to a deeper question that won't go away. As we get better at reading these hidden oceans from afar, how much of their reality will always remain invisible to us? Where is the line between what gravity and magnetism can reveal? What will forever stay below our observational horizon? That line isn't just philosophical, it's practical. Because to study Europa's ocean, we're forced to do something very human and very risky. We have to turn physics into a detective novel. So, let's start at the very beginning of that process. You get a few hard measurements. Europa's mass and radius from its orbit and how it tugs on nearby moons. Its overall density, telling you ice on the outside, rock and metal deeper in. Magnetic field signatures from Galileo, whispering that a salty conducting layer is sloshing under the ice. Surface features you can literally photograph. Cracks, ridges, chaos terrains that look like shattered sea ice frozen mid-storm. From that, you don't get a picture. You get suspects. One model, a thin ice shield, maybe 5 to 10 kilometers thick, floating on a deep global ocean. Another, a much thicker shell, 30 kilometers or more, with pockets of liquid trapped inside. Both can match the same gravity data. Both can produce chaos terrain. Both can live under the same brutal radiation from Jupiter. This is where the detective work kicks in. A good detective doesn't just list clues. They build a story that connects them. Planetary scientists do the same, only their witnesses are equations. Heat flow models say tidal flexing in Europa's interior should keep an ocean liquid for billions of years. Induced magnetic fields say that ocean has to be salty. Surface chemistry says radiation is constantly remixing the top few centimeters of ice, dragging traces of the ocean up and shoving processed material back down. Because here's what nobody tells you, multiple stories can fit the same clues. One story has vigorous convection in the ice, brine channels, maybe even hydrothermal vents at the seafloor. Another has a more stagnant lid, a colder, quieter ocean, still global but less friendly to life as we imagine it. Both are consistent with the mass, the radius, the magnetism, the cracks. So which one is true? New missions act like fresh witness interviews. Europa Clipper will fly through Jupiter's magnetic environment again and again, tightening the measurements of that induced field. Slight changes in Europa's gravity as the spacecraft orbits will reveal how the interior flexes, hinting at ice thickness and ocean depth. JUICE will add its own angle from a different orbit, a different plane in space. Each new data set doesn't hand us the answer. It crosses out entire chapters that can't be right and sharpens the remaining ones. And yet, something is above the planets. Something is below them. In planetary science, knowing often means shrinking the library of plausible Europas, not discovering a single, perfectly detailed blueprint. We end up with a family of interiors that all fit the clues within the error bars. So here's the uncomfortable question. When we say we know Europa has an ocean, what are we really claiming? And if our best theories will always be, at some level, educated detective work, how bold should we be about what we do next with this hidden world? So if our knowledge of Europa is really a set of best guesses, that leads to a much sharper question. Not just what should we do next, but what do we have the right to do next? Because here's what nobody tells you. Europa isn't just a science target. It's an ethical minefield orbiting Jupiter. On one side, you have this deep, almost gravitational pull to explore, to crack the ice, to drop a camera into that black water, and finally see what's swimming there, if anything. On the other side, you have a responsibility to protect what might be the only untouched ocean biosphere in the entire solar system. If there is life down there, it has evolved for billions of years without us. No radio signals, no rockets, no plastic, no metal shards from broken probes raining down through the ice. Just chemistry, tides, and gravity, slowly writing a story in the dark. Do we have the right to barge into that story with a hot drill and a nuclear-powered submarine before we even understand the first chapter? That's the argument for restraint. We already know how good we are at accidental contamination. We found terrestrial microbes clinging to spacecraft, hiding in clean rooms, hitchhiking on every mission we launch. Now put those passengers into a sealed ocean that might hold more water than all of Earth's oceans combined. If they get in, we can't pull them back out. We could erase an alien ecosystem before we even recognized it as one. And yet, something is above the planets. Something is below them. Our curiosity sits above the ice, and a whole world of unanswered questions waits below. Direct access to Europa's ocean could tell us whether life is a cosmic fluke or a common outcome of physics. It could show us new biochemistries, new ways planets move heat and chemicals, new clues to how Earth's own oceans began. You know, the one question that keeps coming back, are we alone? Right now, our technology quietly forces us to be patient. We can orbit, we can fly by, we can read magnetic fields and gravity like a detective reading a crime scene. But we cannot yet punch through tens of kilometers of ice in that brutal radiation. Our limitations are buying us time to argue with ourselves before we leave a permanent mark. So here's the pattern interrupt. Imagine it's 50 years from now. You're sitting on a mission planning committee. The engineers slide a perfect rendering across the table. An ocean-penetrating probe, sterilized to the best standards we have, capable of melting through the ice and sampling the water directly. There's one agenda item: One vote. Do we send it, or do we decide that some oceans in space should remain forever unseen? Now, let's begin to imagine what it would actually take to reach that hidden water without destroying the very secrets we're trying to uncover. So here's the uncomfortable twist in that boardroom scenario. There's a real chance the vote never goes our way. Not because we lack imagination, but because the engineering, the ethics, and the physics all line up on the side of caution. We're talking about melting through up to 30 kilometers of irradiated ice, keeping a probe sterile in a place where a single terrestrial microbe would be a cosmic scandal, and doing it all with power sources that have to survive Jupiter's brutal radiation belts. You can feel the gravity of that decision, right? Because here's what nobody tells you. Let's just send a submarine is the easy part. Building one that doesn't contaminate a possibly living ocean, that can't be repaired, that has to work the first time in a place we can't visit twice. That's the hard part. There's a version of the future where we look at the risks, the cost, the time, and we quietly decide that Europa's ocean will stay a theory we never puncture. So what does science do if the door stays locked? It does what it's always done when the universe refuses a direct look. It gets clever. We squeeze more information out of the ice, out of the magnetic field, out of tiny wobbles in Europa's orbit. Galileo already showed us that induced magnetic field, that whisper of a salty global ocean conducting electricity under the shell. Europa Clipper and JUICE will read those whispers in far higher resolution, mapping how the field changes as Europa moves through Jupiter's magnetic cloud, and using that to sketch the ocean's depth and salinity. We read the surface like a crime scene. The chaos terrains, the ridges, the fractures that telescopes can see from Earth, all become clues to how thick the ice is and how often the ocean below pushes upward. We compare Europa's invisible sea to Earth's deep oceans, to hydrothermal vents where sunlight never reaches, to other ocean worlds like Enceladus that do throw their water into space. And yet, something is above the planets. Something is below them. In the same way, something is above Europa's ocean. And we can learn about the water from the scars on that bright, flat plane of ice. So, let's start at the very beginning of a different mindset. Some parts of the universe will always stay off limits to direct cameras. We will never stand inside a black hole. We will never scoop the core of Jupiter into a lab. But those regions still shape our equations, our models, our late-night arguments about what reality is. Their power doesn't depend on us seeing them. It depends on them existing. Not seeing Europa's ocean doesn't erase it. It just forces us into a different relationship with it, one built out of inference and imagination. We become the people who can map tides from magnetic flickers, who can picture currents from surface chemistry, who can feel awe for a sea we only know by its fingerprints. And yet, before we sign that emotional treaty with a forever hidden ocean, there's one more picture we have to hold in our heads. What if the vote goes the other way? What if, just once, we actually get to drop a camera through the ice and watch Europa's hidden sea open up around us? So let's cash that fantasy in. Let's actually drop the camera. Now let's begin with a picture you can hold in your head. The engineering arguments, the ethical debates, the planetary protection meetings that go on for years. In this thought experiment, we've done the work. We've solved the power problem, the drilling problem, the sterilization problem. We've threaded the needle between curiosity and caution, and lowered a small, utterly clean probe down a narrow borehole in Europa's ice. It descends for hours. Just ice. Wall after wall of ancient, fractured, refrozen ice, scraped in grayscale by a ring of hazard lights. The probe swings slightly on its tether as local gravity tugs and Europa's slow rotation shifts the line. You feel every meter because you know what's waiting at the bottom. Or rather, you hope. Because here's what nobody tells you. In a world like this, the most dramatic moment isn't the first alien creature. It's the first change in sound. The quiet thud as the drill breaks through. The sudden absence of resistance. The readouts flicker. Pressure equalizes. The probe's cameras tilt down toward a darkness that has never, in 4.5 billion years, seen a single photon. Then it slips free. For a heartbeat, there's nothing. Instruments saturate. Gyros hunt for a frame of a reference where there is no seafloor in sight, no surface above, just free fall in a slow, alien ocean. The lights ramp up from red to white. The beam catches suspended ice crystals, tiny shards drifting like a frozen snow globe turned in slow motion. You watch grains of rock and salt spiral past, tracing faint currents you can't quite see. The camera pans. The ocean is not blue. It's ink. The only color comes from the probe's own LEDs, scattering off microscopic particles, off wisps of what might be organic molecules, or just chemistry doing what chemistry does under gravity and pressure. You know the one. The moment in every documentary where the music swells and the narrator whispers. Except this time, you're the one holding your breath. We steer toward a shadow on sonar. The lights rake across a rocky outcrop, a crack in the ice above, a plume of warmer, mineral-rich water rising from below like smoke in reverse. Do microbial mats cling to those rocks, turning chemical gradients into metabolism? Do we see faint veils of life, or only bare stone sculpted by physics alone? In space, there's no up, there's no down. And yet something is above the planets. Something is below them. Here, that same logic folds inward. Above and below are just directions in a black, pressurized sphere. Here's the twist. Even if the scene is boring by movie standards, no glowing alien forests, no schools of translucent swimmers, just water, salts, rock, and heat, this is still a revolution. Reaching any hidden ocean in the solar system at all would mean we've turned a flat diagram into a place we can enter. It would prove that the barriers we draw, ice shell, radiation belt, distance, are engineering problems, not permanent walls. And yet, as vivid as this feels, it's also a reminder of how far away that first light really is. Right now, we're still stuck above the ice, inferring oceans from magnetic whispers as gravity measurements and the chemistry of a processed, radiation-blasted skin. So in the next part, we have to step back from the fantasy and look at the reality, what we can actually do from orbit, and why Europa's ocean remains, for our era, almost perfectly hidden. So let's rewind. Back at the beginning of this episode, you had a very clean Europa in your head. A neat, layered cross-section, bright white ice on top, a smooth blue band labeled Global Ocean, then gray rock, then an orange metallic core. You know the one. The kind of diagram that looks like someone sliced a perfect cosmic jawbreaker. In that first picture, everything feels mapped. The ice is a crisp shell with a number on it. The ocean is a single, uniform layer with a depth you could print on a poster. The rock is just rock, and the core is just core. It's the same vibe as those flat solar system diagrams, where every orbit is a perfect circle in a perfect plane. Simple, comforting. Wrong in all the important ways, because here's what nobody tells you. Of all those layers, the ice is actually the honest one. That bright, high albedo surface, we've stared at it from Earth with telescopes, from the Galileo spacecraft up close, and soon from Europa Clipper and JUICE in even higher detail. We've mapped the cracks and chaos terrains. We've watched how light at different wavelengths reflects off the ice, picked out water, salts, maybe organic molecules. The ice leaves scars we can photograph, patterns we can trace, spectra we can argue about late into the night. So when we talk about Europa's ice shell, we're talking about something we've really seen. We know its texture. We know it's geologically young. We can measure how smooth it is compared to other moons, how bright it is compared to almost anything else in the solar system. For a frozen world in deep space, that surface is shockingly accessible. Now put that next to what we know about the ocean. No one has seen it. There is no picture, no direct profile, no probe swimming under the ice. Instead, we infer it from an induced magnetic field tugged around by Jupiter, from tiny wobbles in gravity during flybys, from surface chemistry that looks like it's been cycled up from below, from heat flow models trying to balance tidal energy and cooling. Does that ocean start 5 kilometers under the ice, or 30? Is it a calm global layer, or a mess of briny pockets, slush, and rock-water interfaces? The key realization is brutal and beautiful at the same time. Europa's ocean is more hidden, not because it's rare or small, but because every tool we have has to fight its way through filters of ice, rock, radiation, and theory before it can touch the water. Our magnetometers read a signal that's been bent by geometry. Our gravity data is smeared over whole flybys. Our chemistry is rewritten by Jupiter's radiation before it ever reaches our detectors. So where does that leave our mental model? Do we throw out the tidy jawbreaker and replace it with a storm of probabilities? Or can we sketch a new picture that's honest about the uncertainty and still useful for the search for life? In the final part, we're going to try to draw that picture. And it may change how you think about every hidden ocean in the solar system. So here's the upgrade. Instead of a flat diagram of a moon with a blue band labeled ocean, we're going to give you a mask. A bright, scarred mask wrapped around a dark, humming volume. Now, let's begin with that mask. Europa's surface is one of the brightest in the solar system. An icy face with an albedo around 2/3, crisscrossed by rust-colored fractures and chaos blocks. You can picture it easily because we've actually seen it. Galileo flybys, Hubble images, even ground-based telescopes can resolve those global cracks and frozen rafts. In planetary terms, that shell is thin, tens of kilometers at most. But in human terms, it's a wall, taller than Everest stacked on Everest, a barrier we can map in exquisite detail, yet have never physically crossed. Because here's what nobody tells you, that wall is the easy part. The hard part is the darkness underneath. Behind the mask is not a neat blue stripe, it's a volume. A global ocean that might hold more than twice the water of all Earth's oceans combined, pressed between ice above and rock below. We know it's there because of gravity fields, because of how Europa flexes in Jupiter's pull, because induced magnetic signals whisper that something salty and conducting is sloshing around. So we're confident about the big headline: global, liquid, salty, in contact with rock. But inside that volume, we don't get a picture. We get probabilities. Imagine you're holding a glass sphere filled with water you can't see. You know it's liquid because it sloshes when you shake it. You know there's salt because you can taste what leaks out, but you have no idea where the currents run, where the warm plumes rise, where the chemistry changes from friendly to hostile. That's Europa. The ocean is a probabilistic space, a three-dimensional question mark. Are there slow, laminar flows or roaring jets along the seafloor? Sharp chemical gradients like invisible shorelines? Towering hydrothermal chimneys? Or just a dull, muddy plain? Every answer is a range, not line. So the most honest mental model looks messy. The ice mask is crisp. The volume beneath is shaded with uncertainties, gradients, and overlapping zones of could be. You know the one, the old textbook cutaway that showed clean layers like a jawbreaker. Replace that with a glowing shell and a dark interior where our labels blur at the edges. And yet, something is above the planets. Something is below them. In the same way, something is above Europa's ocean, and something is below it. But our knowledge isn't symmetric. We see scars on the mask. We infer whispers in the volume. This matters for life. We're not just hunting organisms. We're learning how to live with important realities that stay hidden behind layers we can only probe with gravity, magnetism, and radiation. The search becomes a practice in humility, accepting that the most promising habitat in this part of space might be one we never truly see, only model. So hold on to that bright mask over a dark volume, because in the next part we're going to ask a harder question. How do you explore an ocean you can't directly picture? And what does discovering life mean when the ocean itself remains mostly invisible? So when we talk about exploring an ocean we can't directly picture, we're not just talking about Europa anymore. We're talking about how we decide what counts as real. Because Europa quietly flips one of your oldest instincts. If you can see it, it must be what matters most. On Europa, the opposite is true. The bright ice, the cracks, the chaos terrains, those are the easy part. Telescopes can map them from Earth. Spacecraft can fly by and film every fracture. But the ocean that might hold life, that's the thing we never see, only feel through gravity, magnetism, and a few chemical hints on the surface. You know the one. The part of the diagram that gets a neat blue band and a label, as if we've actually been there. Because here's what nobody tells you. Our diagrams are not reality. They are negotiations with ignorance. When we draw Europa as concentric shells, thin atmosphere, ice, ocean, rock, core, we're taking a wild, disciplined guess and then wrapping it in clean lines. The ice looks crisp and certain. The ocean looks like a simple layer. The messy part, the uncertainty about thickness, salinity, circulation, gets flattened into a single color. We do this all over science. We draw the solar system as a flat plane, even though the orbits are tilted and the Oort cloud is a swollen sphere. We sketch Earth with a tidy crust, mantle, and core, even though no one has drilled more than a pinprick into the crust. We shade in dark matter around galaxies as if we're fog, even though we only know it's there because gravity pulls on what we can see. The picture is useful, but it lies by omission. Europa forces us to live in that omission. To say, we will never see this ocean directly, and yet we will treat it as real. Because the induced magnetic field, the way the ice flexes under Jupiter's gravity, the energy budget all scream that something liquid is down there. Are you comfortable with that? With truths that arrive only through inference? Now let's begin to notice how that discomfort changes you. Learning to accept Europa's hidden ocean is like training a new sense. You start to respect partial knowledge. You stop demanding a photograph before you believe in a world. You realize that we haven't seen it is not the same as it isn't there. In a universe where most of the mass is dark matter and most of Earth's deep ocean is still unmapped, that's not a philosophical luxury. It's survival. Here's the pattern interrupt. You could look at Europa and feel frustrated that the universe keeps hiding the good parts under ice. Or you can flip it. You can stand in an age of high-definition maps, 4K flyovers, and precise gravity models, and still know that just beneath that polished picture, there are oceans, literal and metaphorical, that refuse to show their faces. And yet, something is above the planets. Something is below them. The secrets are still there. That's not a failure of knowledge. That's the part that keeps the story worth telling. So let's come back to the paradox we opened with. You can see Europa's ice in almost ridiculous detail. You can pull up a 4K flyover, trace every crack with your finger, zoom in until the ridges look like veins on a marble. And yet the ocean that might hold the most accessible alien ecosystem in the solar system, that part is still a shadow, a calculation, an echo in the data. Because here's what nobody tells you. We never saw Europa's ocean in the way you see that blinding white ice. We inferred it. We listened to Jupiter's magnetic field, watched it twist and wobble around Europa, and realized something salty and conductive had to be sloshing under the crust. We weighed Europa with gravity measurements and found the numbers only made sense if a global ocean wrapped the rocky mantle. The surface is a photograph. The ocean is a physics argument. Now, let's begin to unpack why that matters for how you picture this world. Light loves the ice. Sunlight hits that high albedo surface and bounces straight into our cameras. Spectrometers read the fingerprints of water ice and surface chemistry. Cracks and chaos terrains literally draw us a map of where the shell has broken, shifted, refrozen. The ice broadcasts its existence with every photon it scatters. The ocean, though, it hides by default. It doesn't sit out in space where telescopes can collect its light. It sits tens of kilometers down, under a shell that might be as thin as a few skyscrapers, or as thick as a small mountain range. We don't argue about whether it's there. We argue about how thick the barrier is, how salty the water is, how it circulates heat from the rocky mantle below. Those arguments are all filtered through layers of interpretation. Magnetometer wiggles, subtle gravity tugs, surface chemistry that's been scrambled by Jupiter's radiation. You know the one, the detective novel where every clue is smudged. So when we say Europa's ocean is more hidden than its ice, we're not saying we know nothing. We're saying everything we know passes through filters, the ice shell, the radiation environment, the limitations of our instruments, and then our own models on top of that. It's like trying to describe the deep interior of a cloud bank just from the way the sunlight glows around its edges. Here's your mental experiment. Pull up that classic Europa picture in your head. Bright, smooth, crossed with rust-colored fractures. Now mentally drop through it. Under every crack, under every dazzling patch, imagine a volume of water larger than all of Earth's oceans combined, stretching down into darkness. No sunlight, just pressure, salt, rock, and gravity quietly doing their work. Does that shift how you feel about those surface lines you can actually see? Because once that picture clicks, you're ready for the next step. Missions like Europa Clipper and JUICE are about to fly through this system and turn some of those filtered hints into sharper answers. And yet, something is above the planets. Something is below them. If this new way of seeing Europa grabbed you, there are real ways you can stay in that unfolding story. And in a moment, will show you exactly where to dive in next. So here's the strange part. You will almost certainly never stand on Europa. Never watch that cracked ice horizon rise over Jupiter with your own eyes. And yet, what you do from right here on this very flat little screen still reaches all the way out there. Because here's what nobody tells you. Missions don't just appear out of the vacuum of space. Europa Clipper, JUICE, the proposals for landers and long-lived orbiters, they all have to fight for a place in the launch queue. They're competing with Mars, with telescopes, with probes to asteroids and the outer solar system. And the quiet gravity underneath all those decisions is public interest. What we choose to learn about shapes what we actually go and measure. If you've stayed with us through magnetic whispers, hidden oceans, and that dizzying picture of orbits stacked above and below the plane, you're already part of that signal. When you understand why Europa's ocean is more hidden than its ice, you're better equipped to spot what matters in the headlines, to ask sharper questions, to keep this world from fading into the background noise. So, if you want more deep dives into hidden worlds and unseen structures, this is where you can actually pull a lever. Subscribe so you don't miss the next time we peel back a layer of the solar system. Hit like so the algorithm's version of gravity pulls this topic into more orbits. Share this with the one friend who always ends up talking about space at 2 a.m. You know the one. And let's turn this into a real conversation, not just a broadcast. In the comments, tell us, what should our next big step be? Do you want to see a Europa lander that drops onto those chaos terrains and reads the ice up close, tasting the chemistry that's been pumped up from below? Or should we first send a long-term orbiter that perfects our indirect measurements, mapping gravity, magnetism, and radiation until the ocean's profile is pinned down in exquisite detail? Which path feels like the smarter move to you, and why? If your curiosity is still buzzing, don't stop here. You can follow this thread sideways to other ocean worlds like Enceladus or Titan, where plumes and lakes rewrite what a habitable zone looks like. You can dive downward into Earth's own deep ocean, where pressure and darkness rival Europa's, and life still finds a way. Or you can go inward, into the physics of planetary interiors, where heat, rock, and water negotiate the boundaries between ice, shell, ocean, and core. Now let's begin a quieter thought. Europa's ocean might stay hidden for your entire lifetime, locked away behind tens of kilometers of ice, seen only through its tug on gravity and its echo in magnetic fields. But the act of trying to understand it already changes you. It stretches your sense of what a world can be. It bends that simple flat diagram of the solar system into a living, layered place. And in that new picture, you and Europa share something. You're both mostly hidden beneath the surface, and both still worth exploring. So that raises an uncomfortable question. At what point does our urge to peel back Europa's ice stop being curiosity and start being interference? We talk about this ocean like a prize waiting for us. Twice the volume of Earth's oceans, sealed under kilometers of ice, stirred by gravity and heated from below. But if there is an independent ecosystem down there, evolving in its own dark orbit around Jupiter, how close is too close? Is the moment we melt through the last meter of ice a triumph? Or the first invasive species event in another world's history? Because here's what nobody tells you when you see those clean mission concept animations. Every drill, every melt probe, every lander carries microbes. We scrub them, we bake them, we sterilize them until they're cleaner than an operating room. And yet something is above the planets. Something is below them. On Earth, life has a way of riding along in cracks, in films, in microscopic pockets you don't even know are there. So if we send a probe down into that ocean, are we exploring it or are we seeding it? One answer is to go extreme on safeguards. Fully sterilized probes, not just heat-treated, but built from the start in bio-bubbles designed so that nothing from our biosphere survives. One-way missions that never come back to Earth, so whatever they touch remains quarantined in Europa's gravity well. Maybe even hard limits on how deep we're allowed to go, the way you might set a no-fishing zone over a fragile reef. We could decide that the first generation only studies the ice shell, reading the ocean by its magnetic whispers and its chemical fingerprints, and leave the water itself untouched. But now, imagine the future headlines. First confirmed alien life found in Europa's ocean splashed across every screen on the planet. You know the one. Blurry image of a strange cell, or a filament, or a colony shimmering in infrared. Now put it next to a different headline, years later. Did 2040's missions contaminate Europa before we detected native life? Which one do you want to be true? Which one do you trust? So, let's start at the very beginning of this dilemma. You, sitting here, are part of the generation that has to decide the rules long before the first drill ever bites into ice. Do we treat that hidden ocean as a laboratory, a wilderness, a museum, or a neighbor? There isn't a simple yes or no here, and if someone gives you one, you should be suspicious. Now let's begin a different kind of exploration in the comments. How close is close enough? What would you be willing to risk to see beneath that ice? And what line would you refuse to cross? Because the hardest parts of exploring hidden oceans aren't just technical, they're moral. And the real test comes when we finally have the power to touch that ocean and have to decide if we should. So let's walk back out to Europa together, one last time. You're standing on that ice now. Jupiter hangs above you like a swollen lantern, banded and boiling, filling half the sky. Under your boots, there's an ocean bigger than all of Earth's oceans combined, wrapped around a rocky mantle, pressed by gravity into a global black abyss. And yet, if you stare down, you see nothing. Just a bright, cracked shell that refuses to give the ocean away. Because here's what nobody tells you. That silence from below, that blank, unlit sea, it isn't a failure of our telescopes or our probes. It's an invitation to build better ears for magnetic whispers, sharper eyes for tiny tugs of gravity, and more patient minds that can accept a picture drawn in hints instead of headlines. From here, the ice looks simple, flat almost. A frozen plain of white with rust-red stains where radiation has chewed through the surface chemistry. You know the one, the postcard image from every Europa article. But beneath that, physics is busy. Salt ions shifting in a global-induced magnetic field. Rock and water trading heat along a hidden seafloor. Tides from Jupiter flexing the whole moon, stirring the ocean like a slow planetary heartbeat. We can trace those tides in the way Europa wobbles in its orbit. We can hear that ocean in the way Jupiter's magnetic field bends and echoes around it. Yet we can't see the waves, or the vents, or the possible life riding those currents. And that's the strange gift here. The ocean stays more hidden than the ice, so we're forced to become detectives instead of tourists. So, let's start at the very beginning of what comes next. If you want to keep following these hidden oceans and buried structures, don't just let this be the last stop. Hit subscribe, stay with us, and then dive into the playlist we've linked on ocean worlds and the invisible scaffolding of the cosmos. Because once you start noticing what's concealed between the bright surfaces, the whole solar system stops being a flat diagram and turns into a layered mystery. Somewhere under that ice, right now, the laws of physics are quietly writing a story in water and rock, whether or not we ever send a camera to read it. There are currents that will rise and fall, vents that will flare and fade, entire chemical dramas that will play out in perfect darkness. And yet, something is above the planets. Something is below them. One moon, one ocean, one thin shell of ice between us and the dark. The universe doesn't rush to show us everything at once, and that slowness is part of why it's worth exploring at all. So we'll leave you here, under Jupiter's glow, with more questions than answers. Fade out with that thought. The richest worlds are the ones that still refuse to fully explain themselves.